no point in using PPT and discussing in the class because this technically mathematics involved. A lot of mathematics is involved in the course. Okay, everywhere you have to derive the equations and substitute. Okay, simplify, integrate, all those things are there. So that's why I use OneNote for teaching, where I will write everything. So that is not my job. Okay, only as a student, you also have to do what I do. That means you have to write everything into your notes. Okay? Everything should be taken down and maintain a well curated notes for the e-transfer course, because that will help you a lot. Okay, in the last moment when you refresh things for exam and all, and once you write it, it will be very clear to you also. And while writing also, you'll get some doubts. You can raise that doubts then and there itself. So better everyone. So there is no excuse for this. Everyone should make a e-transfer notes. Okay, write the things down. So again, when you come to ask doubts, okay, it based on your notes. If you are not bringing your notes and coming to that doubt clearing class, then that shows your attitude towards this course, right? You took it very lightly, and then you end up with many doubts. No, that cannot be entertained because you showed that very clearly that, okay. So I'm telling you, I'm warning you in the beginning itself. Okay, write your notes clearly. Write down everything. Okay, so that's again the two-way communication here. Like when you give a good feedback of by listening to what I say in the class, okay, following my instructions, okay, then I will also be more motivated to help you. But if you don't respond to my instructions, okay, if you take it lightly, then you know what is the feedback you are giving to my teaching. So then I have to reflect that, right? That is very common because we are all humans. So with this, I will start. So I think that is enough. You know now you are not a first year students, you are in third year, okay, sixth semester. So you know all the consequences, or you know all the difficulties involved in engineering subjects, okay. So you have experience, okay, you are experienced students, so I will not tell you much more. And so take care initially itself, write everything properly, maintain a proper notes for the subject, okay. And whenever you get a doubt, don't keep it back or for the end. Clear it and move forward, okay. So now why we start with the this course with the equation, right? So last class I gave many examples, and I introduced the three modes of heat transfer and the few governing laws. Okay, right? What are the three modes of heat transfer we have discussed? Yeah, anybody can answer.
Conduction, convection, radiation.
Conduction, convection, and radiation. Okay, and then we also discussed the three laws. Okay, in radiation we have more than you have. Again, there are other laws. Okay, Kirchhoff's law and all. So that we will see later. But for conduction, what is the governing law? Conduction heat transfer, what is the governing law?
Fourier.
Yeah, Fourier law of conduction. Okay. For convection, we use Newton's law of cooling. Okay. So now we know the laws, okay, of physics that is used in the conduction. So we have we cannot do just with a law of physics. Okay, we have to apply that to the physical problem. Okay, we have to apply the law of physics to a physical problem, and then we end up with a mathematical model or a governing equation. So that's what we are doing now. So we apply the laws of physics, and we obtain the equation governing the heat transfer. Okay. So to derive that, this equation, first we use the conservation of energy principle. Okay. Along with that, we use the Fourier law of conduction. So you can take up any example. Okay, you take a solid metal piece or a metal rod. Okay, or a portion of wall of a furnace. Okay, so you have the problem of heat transfer there. So you can study this type of problems using by applying this energy conservation principle and the governing law for heat conduction, or your law of heat conduction. So I will take much general example, that is I think you can see what is that. Okay, so I took a very practical example for you. You might have seen this in your, everyone might have seen. So cooking potatoes. Okay, what do you do? You put a, if you want to cook the potatoes, you put the potato in the boiling water and wait for sufficient time so that it will cook from outside to inside. So to ask you a few questions now, how long you have to wait? Right? You took a potato and you put it in a boiling water. Now question is how long you have to wait, right? That involves engineering now. Yeah, isn't it? Any factors you think of how long you have to wait? What it depends on what?
I don't get it. You repeat.
No. Okay, you can see the picture, right?
Can be conducted through water.
Yeah, it is conducted from the water to the potato. Okay, right? It's
Number of potatoes.
Number of potatoes. Okay.
Volume of potato.
Okay. It's the volume or the size of the potato. That is more important, right? As long as you are keeping the water at the boiling temperature. Okay. So then the size of the potato, that matters. The time required to cook it. Okay. If you have small potatoes, small size potatoes, then it will cook faster. As the size becomes large, okay, you have to keep it for longer time. So that means, so if you are smart enough, okay, while cooking, you have to see that all the potatoes are of the same or the same range or size. Okay, that means you can see that all the potatoes will be cooking at the same time. But if you put a small potato, very small potato, and a very big potato in same bowl, then you're going to waste the energy, right? Because the smaller one will cook faster, the bigger one takes more time. So this is how the engineering works. Okay.
So
yeah.
So yesterday, last class, you said that in absence of fluid motion, heat transfer between a solid surface and adjacent fluid is only through conduction.
Yes.
Now, when the water starts boiling, will there still be conduction or will it be convection?
Convection. So in water, okay, the heat transfer from the boiling water to the surface of the to the potato is by convection.
So we are considering only till it starts boiling.
No, you are not concentrating. You are concentrating on the water, boiling water. That is not what I intended in this class here. I am taking the potato as the material for the study. You understand?
No, sir.
Okay, so if you want the boiling water okay, from boiling water to the potato. Heat transfer is by convection. But inside the potato, look at inside the potato, how the heat transfer takes place.
That will be conduction.
Conduction. That is what I am bringing that here. Okay. So we will take up the convection in the next chapter, right? So we will now concentrate on the cooking of potato or the heat transfer inside the potato. Okay. Got it?
Yes, sir.
Okay. So now that is purely by conduction. So rate of conduction inside the potato is to be analyzed. So how you do that? How can you analyze the heat transfer into the potato? A crude approximation we can do is that since the potato is in the boiling water, okay, that outside surface temperature is we can take as a 100 degrees centigrade, right? And then it start diffusing into the potato and it starts cooking slowly from the surface. So that means you will have a temperature gradient. How come? What is the meaning of temperature gradient?
Variation.
Gradually changing.
Yeah, you have the higher temperature at the surface and the core or in the core of the potato temperature is still room temperature. Okay, because you kept your potato was at room temperature initially. Everywhere inside the potato temperature is same, and you put it in the boiling water, and the surface temperature came to the temperature of the water. Okay, and slowly the heat started diffusing. Diffusion or the conduction is same terminology. Okay, I have told in the last class you have another term for the conduction is diffusion, heat diffusion. So because there is a temperature gradient, outside temperature is high and inside the potato temperature is low, so there is a temperature gradient. Because of that, heat enters into the potato and slowly the temperature inside the potato increases. And it's a time function. Okay, with the time, the temperature diffuses more into the core, and finally, if you wait for sufficient time, the entire potato will be at the same temperature of boiling water. Okay, so now that is the problem. We can take this as some physical problem, and we can do the analysis. Okay, so how to do that now? You have two approaches for this analysis. You can use the differential approach or you can use integral approach. The integral approach is more easy to understand, okay, but it involves the mathematics of the vector calculus. So that is little difficult for the students from mathematics background. So that's why in the notes they use the differential approach. Okay. So anyway, I'm going to give you a bird's view there at the end for about the integral approach also. So in the differential approach, what we do is we slice this potato into fine cubes or cubic elements, right? You know how to cut the potato to make small cubes, right? So how you do it? How you cut the potato?
Slice it
Yeah.
middle and
So
then
you have to use 3 strokes or chopping directions. Okay. So you cut along X, along Y, along Z, so that you will have. So depending on number of sections you make in each direction, so you will have number of pieces. Cubic. You are making equal number of divisions in each direction. Say 10 divisions in each direction, X, Y, Z. Then you'll have 10 to the power 3 pieces. If it is a perfectly this one, shaped potato. So you can now imagine of that cubic piece, okay, small piece of the potato, right? Is it possible? Could you imagine that? I can cut horizontally like this, okay. Also vertically, I can cut So there are three ways. So we can cut like this vertically down. Okay, we can cut the potato in this sections, and also we can cut the potato vertical. Okay, other direction, horizontal direction, that is like this, like, okay. So this one is coming down in stroke. This is going this direction stroke, and again this is vertically. But all the three direction you have to cut, and you will get the small cubic pieces. So that we can take it as an element of the potato, that will be considered as a differential element, and we can apply the conservation laws to that and obtain the governing equation. So now let's take that one piece of the potato. So what you see here is that cube, small element of the potato, and for that we will write the heat balance, so energy balance. So how do you write the energy balance? For that we use the first law of thermodynamics. To a closed system. Why is closed system? We apply this first law of thermodynamics to the closed system, or we have, this is nothing but conservation of energy principle. Conservation of energy principle. So you can see that you followed my this one, right? So we are taking off a small element of the potato, and we are writing the energy balance for that. So first law of thermodynamics tells us that, what is that? Change in energy of the system is nothing but energy into the system minus energy out of the system plus energy generated within the system. Is it difficult to remember? Right, you know already, you have studied this one in thermodynamics. And you have to understand why I have taken a closed system. It's not an open system. Okay, because the mass of the system will remain same. Okay, so the piece of the potato, that mass will remain same. So only the energy is entering into the element and or leaving the element. Okay, so now you know that why I have taken this this one piece of the element, and you might be knowing, telling me that there is only energy entering. Why should I consider energy out? Is it any question? Anybody is getting that question in mind?
So could you repeat why is what?
No. Do you understand why energy in and energy out term has to be considered here?
Yes, sir, because some heat
Yeah.
is entering the potato piece, some is leaving.
Yes. Okay. Because if the potato, depending on the place, right? If the potato this piece is near the skin, then you know that the heat enters in one direction. Once the temperature of that piece increases, then it will be transferred to the next, like this. Okay, so there is a heat in out also involved. So now you can see that piece of potato as a 6 phases, and through this 6 phases, the heat can enter and it can also go out. We don't know. Now, which phase the heat enters, which phase the heat leaves, we don't know anything. Okay, but generalize that we take that left phase, which is perpendicular to the x-axis. Okay, we say that heat enters. Okay, the quantity is qx, and heat leaving the phase which is perpendicular to x-axis on the right side is qx plus delta x. Basically, what is this subscript x plus delta x means?
Delta X is the energy absorbed by the potato piece.
No, I'm talking about subscript x delta x.
Heat transfer at the phase x and phase x
This
plus
is nothing
del
but the
x.
coordinate. Okay, nothing has, it has to do nothing with the this one. It just tells you the location. I'm sorry, oh, there's some problem with the OneNote. Just a moment. Is it visible now?
Yes, sir.
Okay. So x is nothing but the location. That's all. Okay, x delta x plus delta x is the location, and this is the location x plus delta x. Okay. Similarly, y location here, and this is y plus delta y. Okay, and the z location. So here it's difficult to show because we are working with on a two-dimensional plane. Okay, so difficult. So this is z location, and this is z plus delta z. That's why I didn't show that even heat transfer in the z direction also. That arrow is not shown because it will be too much in that small figure, and you cannot differentiate those things. So that's why I didn't show there. But okay, we have also it entering in the z direction here, qz, and it leaving in the z direction, qz plus delta z. So it subscript is just the shows the quantity at that location. Nothing, it has nothing to do. Okay, but the arrow mark we have put it without knowing which direction heat transfer is taking place. But simply we need is the net quantity, so don't worry, it will work fine. So qx is the heat entering, qx plus delta x is the heat leaving in x direction, qy entering, qy plus delta y is leaving, and qz is entering, and qz plus delta z is leaving. Okay. Now suppose the quantity that if the we put a wrong arrow here, right? So what will happen? Any problem is there in our understanding?
No, so just the sign changes.
Yeah, just the sign change. That's all. That's a good thing. Okay, so that will have a negative sign. That's all. Okay, so that will take care of that. Okay, so we have to now write all those details in the equation. Substitute what is entering, what is leaving. We know now. So just substitute into this one. And for generation, heat generation, we use another term, Q generation. So this is nothing but rate of heat generation per unit volume. Rate of heat generation per unit volume. Okay. So this quantity will be used to estimate. So generally, if you consider the wire carrying current, after sometimes its temperature will increase. So we can find out what is the temperature or rate of heat generation because based on the resistance of that wire. Okay. So based on the resistance of the wire, we can estimate the rate of heat generation. So similarly, if there is a chemical process, okay, we will have the some equation to estimate Q generation. Okay. So that is will be taken care by the heat generation. Generally, it will not be always there. So some cases, as I told you, if you are analyzing something which is carrying heat energy, sorry, the current or some that time only we have. Okay. So for the potato anyway, it's not there, but generally for generalization, we will keep it. So now our this one, what is the change in energy of the that element? That we have to first find out. So how to estimate that? How to estimate change in energy of the element, delta E of that element? Come on. For that, we should know how much temperature of how much the T has increased over a period of time, right? So if initially temperature was room temperature, then after some time delta T, its temperature is more than room temperature. That means there is an increase in temperature of the element as a whole. So that is nothing but the increase in energy of the system. Okay, understand clearly? Delta E of the system is nothing but the energy increase. So we can simply write m dot, sorry, not m dot, mass of the system, m into Cp into change in temperature. That is the increase in the energy of. Okay. So every term is clear now. So we will now go and substitute one by one. Now make few assumptions here. That one is.
Excuse me, sir.
Yeah.
What is E gen?
E.
The third term, E generation. Yeah. Generation of energy, the heat energy. That's what I told you, right? Q generation is the rate of heat generation per unit volume. Yeah.
Okay. So using this quantity, we can obtain this heat generation, rate of heat generation. For example, this is nothing but for unit volume, you have this much heat energy generated. So if you multiply the volume of this element, you will get the heat generation. That's all. Any problem here?
No, sir.
No.
Okay. Yeah. So we will now apply a few assumptions that we make is here. Okay, so we will do it generalized. Okay, so Kx, Ky, and Kz are the thermal conductivities in X, Y, Z directions. That is, I think you can see in the here itself. So I have shown you here Kx, Ky, and Kz are nothing but the thermal conductivities in each direction. So we are keeping it general. That means we will generally, if the material is homogeneous and isotropic, then you have Kx equal to Ky equal to Kz. Okay, that is same thermal conductivity in all the directions. But to make it general, I have kept it different. And what about this one, Ax? So this I can write it here itself. So heat conducted in X direction, and this is from the Fourier law. Yeah, I have to mention here, Fourier law. That is, we saw in the last class, Qx equal to minus Kx A dt by dx. So Ax is the area of heat transfer. So can you tell me what is Ax? For this element, what is Ax?
Delta y.
Del Z, del Z.
Del y, del z. Okay, delta y into delta z. Why? Because that is the area perpendicular to the flow direction. Okay, into dou t by dou x. Similarly, you can write ay delta x delta z, dou t by dou y, and also this is minus kz delta x delta y dou t by dou z. Again, you have to understand here partial derivative, because in our analysis temperature is function of x, y, z and time. Okay, so there are 4 independent variables on which our dependent variable temperature is depends on. So that's why everything here is a partial derivative. Okay. Yeah, now we can write the equation. So I will say let delta T be the increase in temperature of element in time small time, okay, in a time delta T. See, this is delta capital T temperature here, and this is time, okay, delta. So then what is the amount of energy increase in the system? Now you have to convert what is the mass of the system element, mass of element. Tell me.
Rho dV.
Rho into volume, right? Rho into volume. So volume you can write as delta x, delta y, delta z. Okay, this is volume. So we can write the change in energy of the system as change in thermal energy of element in delta T time. Just write delta E equal to rho into delta x, delta y, delta z into Cp into delta T. Okay, that is all. So you write, okay, let me write this equation as the Roman 1, and this is small 1. Now 1 by 1, okay, energy in, what is energy in?
Qx, Qy,
Qx.
Rate of energy or I think I should not use rate now. So thermal energy into the element in delta T, because I am multiplying by time. Okay, so E in is nothing but heat entering in x direction, heat entering in y direction, heat entering in z direction into delta T. Okay, these are rates. Okay, the rate of heat flow into time you have to multiply, so you'll get the energy in. Similarly, energy out. Okay, E out. What is the quantity going out? Is Q x plus delta x, Q y plus delta y, Q
Z plus delta Z into delta T. Okay, and the heat generated, thermal energy generated is E generation equal to Q generation into volume. Okay, into volume delta X, delta Y, delta Z. That is the rate of generation into delta T. Okay, so that is how we can write the equations here. 2, 3, 4. So all the things are known now. So substitute into equation and simplify. So any doubt here? This is the energy change in the element. This is the energy that is entering into the element. This is the energy that is leaving the element. And this is the energy generated within the element. Okay, for a small time delta T. Right. So Qx is entering, Qy is entering, Qz is entering. Whereas Qx plus delta X, Qy plus delta Y, Qz plus delta Z, they are going out. In addition to that, we have a term Q generation. So because of that, the energy that is generated within the element in that small time delta T is this much. So substitute and we can simplify the equation. So substituting in 1, Roman 1, okay, all the 1 to 4 you substitute there and you can write rho Cp, okay, delta T into, I'll write the volume also, okay, delta X, delta Y, delta Z. Is it okay? Rho Cp delta T into delta X into delta Y into delta Z. And then you have to subtract these quantities, right? E in is positive, E out is negative. But what I will do is I'll combine this together and I'll write Qx minus Qx plus delta X, then Qy minus Qy y plus delta Y, Qz minus Qz plus delta Z, and you have to multiply by delta T there. Don't miss that. Then the generation quantity, Q generation, that is Q generation into delta X, delta Y, delta Z into delta T. Okay, so this is almost done now. Now only thing is we have to apply because we have to apply Taylor series to this term, okay, for the expansion of Qx plus delta X.
So
yeah.
So time multiplication left hand side.
Well, why time multiplication for this term?
Have you not written a rate for that?
No, it's a total energy increase in that time delta T. Okay, these are rates. Q is the rate. Okay, that's why we are multiplying by delta T. Generation is the rate, watts per meter cube. This is all these quantities are in watts. Watt is joule per second, right?
Understood.
Yeah. Okay. Now we have to use the Taylor series. So you know Taylor series, right? Using we can approximate Qx plus delta X approximation. You see that not equal to sign, but a tilt. Okay, tilt and line there. That is what you have to use. It's not exact. Can be written as Qx plus tau Qx by tau X
into delta x. So we can approximate this. Is it okay for you? Should I write the Taylor series and then tell you what is what? Or are you familiar?
Yes, sir.
Okay.
Understood.
So understood, right? Because if you have a function f of x, okay, and you can write the function value at x plus delta x if you know the function value at x. So you can write what is the value here, that is f of x plus delta x with using the Taylor series. So that's what we are doing. So we have a qx is a function of x. So the Taylor series we can write here is f of x plus delta x. Tell me. F x is function of x alone, so we can write the total derivatives. Come on. What is f of x plus delta x?
F of x plus
F of x plus
x times f dash x.
d of df by dx or f dash. Okay, no problem. Into
Delta x.
x by 1 factorial. You don't have to write 1 factorial, but okay. Then d squared f by
Squared, yeah, second derivative, second order.
derivative.
Del x.
Yeah, delta squared
2
x
factorial.
by 2 factorial. This is an infinite series, right? It's an infinite series. So it will have how many terms? Infinite. So you can go on writing all the terms up to infinity. But what is the advantage here is as you come closer and closer to x, or your delta x is very, very small. If delta x is very, very small, okay, the condition is that this condition only. If delta x is very small, okay, then we can neglect. We can neglect second and higher order okay. So that means you can neglect this based on the condition, and you want to know that if your delta x is very small, for example, if your delta x is equal to say 0.001, what is the value? It is 10 power minus 3. What is delta x squared?
10 to the power minus 6.
10 power minus 6. You can see that. Okay. So that means that this term is became very, very small. So you are multiplying to a quantity with a very small term. So this quantity becomes much, much smaller. So that is the thing we have to keep in mind always. We cannot make the approximation, or we cannot say that we can neglect this term for a large value of delta x. Okay, if it is 0.1, then still this quantity is big, larger. We cannot simply neglect. So under that condition only we can neglect, and we can say that only we will retain this one, and that is what we have done here. Check it. Okay, q of x plus delta x approximated as qx. Okay, plus okay derivative into. So that's the as what we will do is that because we have taken a small element, for that we can apply the Taylor series and we can approximate this one. So this means we can apply to all the directions. I will not write for y and z here so directly. So I will take up the substitution here, qx minus x plus delta x. What do you get now? So therefore you can write qx minus qx plus delta x. What is this quantity? Just qx. Yeah, qx minus, I'll write, okay, minus dou qx by dou x into delta x. Is it okay?
The minus minus, so this cancels out, and you will end up with this. Okay. So that means for x, this will retain. For y, can you tell me? Similarly, you can write qy minus qy plus delta y. You can write it as, come on. Is it difficult?
Dou y into delta.
Yeah, right. So dou y, dou qy by dou y into delta y. Similarly, you can write qz minus. Okay, now go back to your equation 5. This is equation 5, and substitute there, and you have the almost done. Your equation is ready, right? So you can write substituting in 5. So you substitute these quantities there, and you can simplify. So rho Cp delta T into delta X, delta Y, delta Z. On the right hand side, you have, what is that? Minus Qx over X minus Qy over Y minus dou Qz over dou Z into delta T plus the heat generation quantity Q generation into volume delta X, delta Y, delta Z into delta T. That's all. Okay, now you go to the figure above, and these quantities are already written here. Qx is nothing but, oh, what happened here? Strange. Can you see this here? Some quantities are deleted. Q, Kx.
So
No?
now can see.
Okay, okay. So some things, the one note. Yeah. So we know this quantities. Now substitute in the place of Qx, you substitute this quantity. Okay. And you can get the final equation. So rho Cp delta T volume delta X, delta Y, delta Z, substitute here. Okay. Minus dou by dou X. What is Qx? Tell me. You have to tell now.
Minus kx,
Minus
kx dou t by dou x.
Delta Y.
Sir, you forgot one term, sir.
Which one?
In top, it should be del x, sir. Del x and then del y and del z in each of the terms.
Oh, sure. Yeah,
So
yeah,
volume
yeah.
won't come, sir, if we miss it.
Thank you. Yes. Here there is a delta X here. There is a delta Y here. Sorry. And there is a delta Z here. Sorry. Yeah, thank you. Okay, delta Y, delta Z into derivative is dou T by dou X into delta X. Okay. The next term here minus dou by dou Y. Qy is minus Ky and delta X, delta Z into dou T by dou Y into delta Y. Okay. The third term minus dou by dou Z into minus Kz delta X, delta Y, dou T by dou Z into delta Z. In put the bracket and delta T is there. Okay, and the last term, Q generation, delta X, delta Y, delta Z, delta T. Okay. Now you will see that everywhere we have the volume same. So you take it out, okay, because it's an independent thing. So we will take it out and it will cancel out. Right. We have delta X, delta Y, delta Z, delta X, delta Y, delta Z. And here also delta X, delta Y, delta Z. So here everywhere that volume is there, you just take it out and remove it. So we can write rho Cp delta T. And what about this minus sign? Everywhere you have negative sign.
Cancel.
Yeah, it will cancel out and you'll have plus. So dou by dou X of Kx dou T by dou X. Okay. Then delta T is there that we have to write later. Okay. Then we have dou phi dou Y into Ky dou T by dou Y. And then last term dou by dou Z of Kz dou T by dou Z. And also Q generation term will come. Q generation in, okay. All will be multiplied by delta T, but I can take that delta T to the left hand side. Okay. So this is my energy equation. Now only I apply the limit. Okay. In the limit of delta T goes to 0. Then what will happen to the left hand side is the derivative. Okay. It will become a derivative. So we can write rho Cp dou T by, okay, and right hand side will be dou by dou X of Kx dou T by dou X plus dou by dou Y of Ky. This is general. Okay. Now if you know that the property K, thermodynamic property K is constant because the material is homogeneous and isotropic, then the K also will come out and you have a very short equation you can write. Okay. So if material is homogeneous and isotropic. Yeah, the problem with one note, if I write it fast, isotropic. Okay, then we can write Kx equal to Ky equal to Kz equal to, we can simply say K. And that is a constant value. It will not need, we don't need to differentiate that with respect to X or Y or Z. And we can take it out of the derivative. And that can be brought to the left hand side. We can write rho Cp by K, okay, into dou T by dou T. And what we have is the second derivative, dou square T by dou X square, dou square T over dou Y square plus dou square T over dou Z square plus you have Q generation over K. See, don't miss this one because when we are taking this K value, there was no K value here. So you have to write Q generation divided by K. Done. So this is my general energy equation. Very simple. So there's a, yeah, it will be time consuming to write every term, but derivation is not difficult. Okay, very simple. So this is the general energy. equation or conduction equation in the Cartesian coordinates, and the quantity rho Cp by K. Okay, the quantity K by rho Cp. So what is this quantity? Actually, it's a material property. Okay, it's a combined. All these quantities are material properties, right? So is known as thermal diffusivity. Okay, thermal diffusivity. And the unit notation used is alpha. Quickly tell me what is the unit of this quantity. Yeah. Thermal diffusivity alpha. Yeah, tell me the unit of this quantity. Why so much time? You have to substitute and see, right? What is the unit?
Meter square per second.
Yes, good. Meter square per second. So anywhere else you have seen this unit?
Viscosity.
Yes, kinematic viscosity. Not you have to specifically tell kinematic viscosity is also as same unit. So it's you should understand here, whatever be the this one property that diffuses, okay, the diffusion constant or the diffusivity is having the same unit, diffusion constant. Okay, kinematic viscosity is also called viscous diffusivity. Okay, the other name for kinematic viscosity is viscous diffusivity. Similarly, we have the concentration diffusion. Or okay, so concentration diffusion constant diffusivity is also as same unit. Heat diffusion is also as same unit. So that means whenever you get this word diffusivity or diffusion constant, it's ultimately as same unit, which is meter square per second. Okay, it shows tells you how far the heat will diffuse into material in a unit time. Okay, so it gives the estimate of rate the depth or depth of diffusion into the material, heat diffusion in a unit time. Okay.
So what's the other name for kinematic viscosity?
Viscous diffusivity. Viscosity diffusion. Okay. Sorry. Viscosity diffusion. So viscous diffusivity. New. Unit is same, meter square per second. So you can write this quantity rho Cp by K as 1 by alpha, and you can write the equation in a short. So you can refer to the heat transfer data and book for the quantity alpha, because it's a combination of thermal conductivity, density, and Cp, heat capacity of the material. Okay. So if you know these three quantities, you can calculate alpha, or directly you can take the value from the table. 1 by alpha into dou T by dou T, and on the right hand side, everything will remain. So this again, those I think you are familiar with the Laplacian operator, delta squared T plus. Is it okay? Anybody knows what is this one?
Nabla dot Nabla.
Ah, Nabla dot Nabla. Okay. Okay, Laplacian operator. So you have studied in mathematics. Okay.
So dou square by dou x square plus dou square by dou y square plus dou squared by dou y z square. So that is the Laplacian operator. When it acts on a scalar quantity, we can simply, instead of writing entire thing like this, we can write in a short. Okay, now you can take up the case of the case where there is no heat generation. Okay, so if there is no heat generation, then you take remove the last quantity, and you have unsteady heat conduction without generation. That means you have only, okay, this case you can simply understand, very simple. Okay, just remove the generation term, and you have 1 by alpha dou t by dou t equal to del square t. And if it is steady state, then you have only steady.
It's equal to 0.
Yeah, heat conduction without generation. With the generation, steady heat conduction with the generation means you have del square t plus Q generation by K equal to 0. And if it is steady state without generation, without generation, then we have just del square T equal to 0. Okay.
So in the second case, dou T is 0. The temperature is not changing.
Where? Which is 0?
Case 2, steady heat conduction.
Yeah, steady heat conduction with generation. What is not changing? It's not changing with respect to time. Okay.
Okay.
But in the space, there is a variation. Understand? Okay, maybe there is a problem with the. Okay, you have to understand clearly here that temperature gradients are there. You have to understand the rate of heat supply will be same, and also there will be some amount of heat is removed on the other side. So there will be a gradient of temperature is there, and that will not change with the time. That's all. But there is a heat conduction. All heat is flowing from a source to the sink. That problems will be there. So with respect to time, anyway, it is not changing, but in the space there is a gradient of temperature is there, and it is constantly flowing. The same amount of heat is flowing all the time. Okay, that is steady state conduction. Okay. Then we can also derive this Gauss equations in different coordinate systems. And in addition to that, you have to understand here that we cannot simply do anything with this Gauss equation. What we need is, what is needed? When you have a differential equation, you cannot obtain the solution unless you have the okay, isn't it?
Yes, sir.
Okay, so it's very important. Okay, you have the Gauss equation, but you need also boundary conditions, and that is not the it will not be given directly anywhere in the problem. You have to analyze the problem and also get the boundary conditions. This is the job of engineers. I mean, think about it.
The derivation of this Gauss equation is done by somebody else in the long back, okay? And we are learning that, isn't it? It's nothing new, we did it in that. But what is important here is the boundary conditions, and that boundary conditions will not be given, okay, by any, or it cannot be generalized. Understand what I am telling? It cannot be generalized until, okay, this is the boundary condition, you can apply and solve it. No, it depends on the problem. Depends on the problem, depend on situation, the boundary conditions will change. And for that, you have to experience, you have to gain the experience to know how to derive the boundary conditions or write the boundary condition based on the practical problem. For example, if I go back to that cooking of potato, what I told you is the initial condition, you can say. What is the initial condition you can write here for this potato? Initial condition. What is the initial condition?
Surface temperature is ambient.
Not only surface temperature, it's everywhere, okay, irrespective of, okay, the position x, y, z, whatever with the x, y, z, but time is 0, then temperature is, say, 30 degrees centigrade or the ambient temperature. That is the initial condition. Okay, our time t is 0, that is the reference time, the moment before putting into that boiling water. This is what everywhere inside the potato, not only on the surface. Okay, any doubt here? Srinivas?
No, sir.
No. Okay, you know that you have studied thermodynamics before this heat transfer, so you will be knowing what is thermal equilibrium means, right? Of course, if you put the potato in the refrigerator and if you put it outside, then you can say that, because there will be difference in temperature, because inside the refrigerator you have a different temperature. When you keep it outside, it will take some time to come to thermal equilibrium with the surrounding. So it's the initial condition. And then what is the boundary condition? The moment you transfer into boiling water.
Surface temperature is 100.
Yeah,
degrees.
surface temperature. Now, temperature at the surface, I don't know x, y, z location. Okay, there is a complex trajectory. And for any time, so S, comma T, I will write. S is the surface. The temperature is 100 degrees centigrade. All, okay, the boundary condition, the boiling water temperature will remain same at 100 degrees centigrade. So surface boundary condition we can apply. And then we have to solve this problem. So this is very important. By knowing the practical situation, we have to write these boundary conditions, and nobody will tell us directly, okay, you have to. In the class, I can tell you, okay, but when you go back, go to your, when you will start working with the heat transfer problem later in your life, you have to deduce or obtain this boundary condition by observing the problem, okay, by observing the problem. And this is by experience, you will know that. So there are different boundary conditions we can give. One is, this is a Dirichlet type, where the temperature directly you mention. Okay, the dependent variable value is directly mentioned on the boundary. Or sometimes we know the rate of heat transfer because we are using some electric heater or something. So we know how much energy is consumed by that electric heater. So from that we can obtain the rate of heat generation or rate of heat input. That is heat flux boundary condition. Heat flux. Okay. So that is, we can directly, we know Q value, which is nothing but we can relate this one proportional to temperature gradient. So if I use some direction, that will be a kind of, you know, very Okay, instead of using that x, y, z, I use a general direction n. Okay, so we can have the gradient of temperature known, and that can be applied in the solution. Okay, so sometimes there is no heat flux. That means no heat flux means there is an insulation. Means what is the boundary condition?
Q surface 0.
Yeah, Q is 0. Insulation, or that is no heat flux. Then dou T by dou N equal to 0. Okay. Understand why N is used? Is a general, okay, X, Y, Z, or whatever. If it is radial, then R you can use. Okay. So there is no heat transfer in that direction. Okay, these are the different boundary conditions we will come across in the heat transfer. So it's very important. Just equation is not enough. You have to write the boundary condition also. Okay, then we can derive the equations in other coordinate systems. So we can use the cylindrical coordinate system and write that down equation. So for cylindrical coordinate system, okay, you can see the Gauss equation. We can derive the same procedure. So use your time, free time. Okay, try to derive this equation so that you will have a good confidence. Okay, to if the question is asked in the exam also, you can do it. Right? What is the thing? Is just we have to take the differential element in the cylindrical coordinates. I hope you can see there, right? So we have to write the three quantities in the radial direction, theta, pi direction, and z direction. Okay. So radial direction, r direction here, and pi direction here, and z direction, axial direction, z. So three quantities, and write the same balance equation and simplify the equation. You will get this. Similarly, you can also do the obtain the equation in the spherical coordinates, right? Spherical coordinates also you can derive the equation. So I don't ask you to spend time on this one, but at least cylindrical you do it. Okay, cylindrical is very easy, not so difficult, as here anyway you have big terms coming because of that control volume. Okay, but you have you can also try, no problem. If you have time, you can try that. Okay, so then that is the derivation of equation in Cartesian coordinates.
So can you scroll up?
Yeah. Okay. You are writing. Okay. Okay.
Cylindrical also.
Cylindrical also. So then the important thing I told you in the beginning itself, the integral approach is the most easiest one and easy to understand. Okay, makes much sense than the differential approach. So I will just quickly give you that idea of integral approach. Yeah.
Scroll down, please. Thank you.
Okay.
Done, sir.
Okay. So same, we have delta change in the energy of the system is nothing but energy in minus energy out, okay, plus energy generated. So here energy in, energy out, we can easily estimate by using the integral approach. Okay. So what do? We take a control volume for this potato. We can take this as a control volume. Right. You have the surface of the potato here. Okay. Now, what is the this one? You can understand here clearly that whatever quantity that is entering into the potato has to go through the surface, right? Whatever heat energy that is entering or leaving the potato has to go through the surface. So, if we define a vector quantity, right? You can take an element on the surface, and the vector quantity is the heat flux. Heat flux, okay. Right, that is the vector quantity. So it can have any direction. It can, we don't know the direction of the heat flux, okay, and the normal vector to the surface there is n vector, normal vector, normal unit vector. So this heat flux, what is heat flux? What does heat flux means? Heat transfer per unit area, okay? Q per area, that's all. Q is a vector, okay? It has heat transfer will take place in particular direction. So this is nothing but heat flux. Okay. So this vector, as I have shown there, it may point inward or outward. So if the heat is going out, then it is pointing outward. But if the potato is, for the case of cooking potato, it should be inward. Okay, heat is going into the potato. Right. So now, what is the thing is, we can, the first thing, this will remain same. The energy inside the potato, you can estimate what is the energy inside the potato at room temperature, and after some time the temperature will increase. Okay, so we can simply estimate the total energy of the potato by integrating, okay, rho Cp into T over the volume of the potato. So this is nothing but the energy stored in the potato. Okay, is it difficult to understand? Right. If you are integrating this quantity in over the entire volume of the potato, you will get the energy stored in the potato. Okay. So then you have to now apply the other part here, which is this one. This together, in and out, can be obtained by vector dot product of these two over the surface, integrating over the surface. So we can get E in net out as, okay, what is that? Just take the vector dot product of the flux vector and n vector over the surface. Now the direction, again, the problem here is the direction, because if you want to write E in positive, then you have to put a negative sign here, because, right, this normal vector always pointing outward. That is the reason why I have to put the negative sign here. So this will give us the net energy that is entering into the potato from the surface. The basic idea here is anything or any quantity that entering or leaving, it has to go through the surface. That is the fundamental thing. Okay. So that means we can capture or we can estimate the energy entering or leaving, net energy entering or leaving, by simply doing the integration over the surface of this quantity, which is the heat flux. Okay, just estimating that heat flux and integrating over the surface area, right? This is
so with minus sign it becomes leaving, right?
Minus sign.
With minus sign it becomes leaving the surface, right? Energy
exiting. No, it is entering. Okay, net energy entering it will become. Why? Because N is pointing always in the outward direction. Always. There is no this one. That is defined like that. Okay. If it is leaving, then these vectors are pointing outward and the dot product is positive. You're getting that? This is also outward and this is also outward, means then the dot product is positive. But if the Q is opposite into, then the dot product will become negative. That's why we have to put that negative sign. That's all. Okay. Now substitute. Each generation is same. So that, okay. So this is the energy inside the potato. Now, if you want to know what is the rate of change of energy, rate of change of energy in the potato, you have to take the time derivative of the energy stored. Okay, so that means you take derivative of this quantity integral over the volume rho Cp T dV. Okay, and on the right hand side you have minus AQ vector dot n vector GA. Okay, and then you have the heat generation quantity, which is exactly we can write integral over the volume Q generation into D. That's all. So this is our simple equation, and just you need to apply the Gauss theorem now to convert this surface integral into volume integral. That's all. Okay. So if you apply the Gauss theorem, and here, since this is arbitrary integration, the volume of the potato can be taken. If I pick the potato, I will pick this one. If I ask you to pick somebody else, you will pick another one. So that means it's arbitrary. Okay, the volume is arbitrarily chosen. So we can take the derivative inside the volume, and we can write as rho is constant, Cp is constant. We can write this as dou by dou T of T dV. Okay, and on the this one, I will keep it as it is now. Then I will tell you to apply the Gauss theorem there. And this is again the volume integral of Q generation into dV. Okay. Now you know Gauss theorem from mathematics, vector calculus. We can convert the surface integral into volume integral, or volume integral into surface integral. Gauss theorem. That is integral A dot N dA can be written as integral, okay, del dot A dV. So you can refer any mathematics book. It's very easy to understand also. Okay. So divergence of that vector field will give the volumetric change in the volume. That same thing should be equal to the that change is because of the quantity entering through the surface. Okay. For anything which is coming out of the surface, actually coming out of the volume. Okay. It cannot be other way. Simply, it says that. Okay. This is nothing but its estimation of the quantity which is net quantity which is leaving or entering the surface from the volume, and this is from the surface. So there cannot be difference in these two quantities. Okay. So that means if I substitute this one, and we can convert this one into volume integral, and we have the equation. that is rho Cp, okay, integral over the volume tau T by tau T d volume. And what will happen here? You can see that A dot N will become del dot, right, over the volume del dot Q vector d volume dV. Okay, then you have the generation term, integral over the volume. Now the quantity Q, I have already told you here, is Q is nothing but, right? So we can write this as, what we can write? Come on. Q we know from the Fourier law, that is minus Ka, or this is the problem here. We have to take the direction. So I'll take the general direction. Now when divided by area again, so area cancels. So this is nothing but minus K dou T by dou N. Or simply we'll write this as N is the normal direction to the beat, not normal. Sorry. This is the problem here if I simply do this way. So better we will write, this is a vector. So we have to write all the three quantities of this vector. Okay. You are familiar with this Ka del T. Okay. Gradient of T. Del is nothing but dou by dou xi okay. So this is a gradient operator. So we can simply write Ka delta del T and divide by area. So area will cancel out there, and we have Q is nothing but minus K del. Okay. So you go back and substitute for Q there, and you have the required equation now. Again, you can remove the volume integral since it is an arbitrary volume. So I can simply write, since V is arbitrary, we can remove that. We can apply for any differential volume, or simply we can write this as rho Cp dou T by dou T equal to minus del Q is nothing but, we go back here, right? Q equal to minus K del T minus K del T, and you have Q generation. Okay, that's all. So this you can simplify. Del K is constant. If you take it out, del squared T plus Q generation, and that's what we got. Okay, rho Cp dou T by exactly same equation. Okay. So
can you scroll up?
Yeah. Up. Where?
Just a little up. Okay, that one.
Okay. Doubt? So if you are good in mathematics, I think it's very easy to understand. Okay, the vector integration, all those things are there, but easily understand. Yashwant Reddy is that. Yashwant, you there? Okay. So the derivation of one equation itself took the entire class. Okay. So
can you so can you scroll up to that case one that I couldn't write that whole
Okay. 1 minute. Struck. K is right. Okay, 1 minute. K is 1, 2, 3.
Yeah, thank you, sir.
Sir, how did you remove that integral sign in the last step?
No, this is because arbitrary integration. Okay, so you can take that. Okay, everywhere it is there. I mean, you can write the equation in differential form. This is the differential form equation, and this is the integral form. It's not like taking out. Both equations are same.
Oh, okay, sir.
Yeah. Okay then. So I will stop today's class. So you have any doubt? Anyway, the last part is not included in your syllabus. Okay, just to introduce you that this one concept I have explained. But if you are going for higher studies, okay, masters and all, then you will see this type of approach. Integral approach is very common and very versatile. Okay, it's very useful also.
Sir,
because later, yeah.
Sir, it should be Q gen by K, right?
Q?
And the final equation.
No, I have not taken K out. No, if it is only when you take that K out and divide that entire quantity by K out, then rho Cp by K will come, which is 1 by alpha, and K will disappear from here, and one.
Yes, sir, I got it. Thank you.
Okay then. So we will start with the simple problems. Okay, one heat conduction in Cartesian coordinate or planar wall, cylindrical wall, and spherical wall in the next class. Okay, and we'll do it. So better you understand, and if you have any doubts, please raise that in the next class. Okay, this should be very clear. Okay.
Thank you, sir.
Okay, bye.
Thank you, sir.
Thank you, sir.
The candidate